Okay, so we have matter particles, the fermions. Now we're on to the other type of particles, which aren't really particles. I know. So they don't make up matter, but they are essential for various forces, including the electromagnetic force, which is carried by bosons of photons. The photons are the force mediating particles for all sorts of forces you will find out and be surprised that you never realized were actually conveyed by photons. There's the strong force, which actually holds the nucleus together, made up of gluons, and I'm not making this up, they are honestly called gluons. And then slightly more difficult are what's called the weak force. Funnily enough, it's not as strong as the strong force, but the weak force is conveyed by these W and Z bosons. It's only the W boson that we're going to be interested in for higher, because that's involved with beta decay. Now, just to remind you that a neutron's got 2 down, 1 up quarks, and a proton is much more positive, and so it's always looking up, so it's got 2 ups, 1 down. We're going to use that in a moment. Because in beta decay, you'll have seen this before with nuclear radiation, you can have, for instance, some radium that converts to actinium. You've got the same mass number, the same number of protons, but one of the neutrons, neutrally charged, converts into a proton. And how on earth do you do that? Because there's a change in charge. Well, we can do that because the transformation from a neutron to a proton produces this electrical electron or beta particle, and also an electron neutrino. That's the neutrino symbol just there. And the weak force is needed to do that. It's going to take a bit of getting used to this. So I've got a slide here that you can read through later yourself, which takes you through beta decay there. So you can go back to that one there. But the main thing is there's a change in a down quark to an up quark. And the only way that can be achieved is through the W- boson of the weak force. And that W- boson produces an electron beta particle and that electron neutrino. And at that point, you've converted your neutron to your proton. But it's this weak force, that's why the weak force is so important there. So there's a YouTube clip here, and we've got initially the neutron coming in, which is in the nucleus of the atom, 2 downs, 1 up, and that has the weak force, which converts one of the downs to an up, but that weak force has to produce an electron and its neutrino. And that's drawn in the way of one of these Feynman diagrams. So you can see the Feynman diagram has got what was going on there. That's coming in, that's leaving, and that's the weak interaction producing the electron and the neutrino. So we can now put in the W boson as one of our 4 bosons here for the gluon of the strong force, the photon of the electromagnetic force, Z boson, which we don't really talk much about, and the W boson for the weak force. The Higgs boson has only recently been confirmed as being one of those bosons, and there's a little video from a BBC program to watch later on about that. So what we've covered is that standard model there. You should now have a better idea of that we've got the evidence for these quarks and things from particle accelerators. The beta decay was actually where we got the idea of the neutrino from. Fermions are made up of quarks and leptons with 6 types of each. Hadrons are made of quarks, baryons are made of 3 quarks. Bosons are quark